What is geometry? What even is a shape? If you find yourself asking these questions, fret not, because I'm here to explain. Today we're going to be talking about polytopes. A polytope is just a shape with flat sides in any dimension. An n-polytope is an n-dimensional polytope. So a 2-polytope would be a polygon, and a 3-polytope would be a polyhedron. This is massively oversimplified, but it's a good start. Let's start in one-dimensional space, also sometimes called 1D or one space. One-dimensional space is simply the set of real numbers. A real number is just any normal number. It can be 0.5 or 3 or -4 or 1 billion or tau over 2, also sometimes called pi. One-dimensional space is very simple. Here there are only two directions, positive and negative. If we have a point here, that's called a vertex. If we have 2 points, we can connect them with a 1D edge, creating our first polytope, the line segment. Shapes are really just subspaces or subsets of space. Remember how we define space as just every real number? Well, we can define this line segment as a set of real numbers between these 2 points. This makes things more confusing, so you don't have to think about set theory if you don't want to, but I think it's neat. And for those who don't know, a set is just an unordered list without duplicates, aka everything is either in the set or it's not. Line segments are a bit of a loser trivial polytope. Hey, what's that thing? Is that a new 1 polytope? Nope, it's a mysterious 2 polytope. The way 2 polytopes, also known as polygons, work is they are made of vertices and edges, but they can have multiple edges, and then they have, or more accurately are, one face. They live in 2D, which, remember how 1D is the set of all real numbers? Well, 2D is the set of all combinations of two real numbers, usually denoted as the set squared. So what shapes can we have? Well, basically anything we want. For a shape to qualify as a polygon, it must be a set of points in 2D that are connected by edges where every vertex has 2 edges connected to it. No more, no less. This is called diadicity. These polygons are cool, but how should we categorize them? Well, symmetry is cool. I like symmetry. So let's categorize them on that. Since 2D is so trivial, there's really only 2 types of polygons. There's the regulars and the irregulars. There's, of course, more, but we don't have time for that. Regulars are pretty complicated to define, so for now I'll just say a regular shape is a shape that is as symmetrical as it can be. Every side is identical and every angle is identical. I'll go more in depth on this later, don't worry. Platonic solids have their vertices lying on a sphere. So in 2D, we can have some number of vertices evenly spaced on a circle, and then connect every point to its neighbors with edges, and connect the whole thing with a face, and boom! We have an infinite number of regular polygons, from 3 sides to infinity. This works because the circle's surface is Euclidean, so it can be divided however much we want. Euclidean just means that it has 0 Gaussian curvature, which may sound weird to say that a circle isn't curved, but it's actually not. Because if you have a one-dimensional entity living on the surface of the circle, it can't tell the difference between a circle and a straight line with portals at either side. Therefore, these two surfaces are topologically equivalent. Something like a sphere, on the other hand, has positive Gaussian curvature, meaning that the inhabitants of a sphere actually can tell that their space is curved, because they can make triangles with more than 180-degree angles. Like, for example, this triangle has 3 right angles, which adds up to 270 degrees. It's actually not possible to make a triangle in spherical space that has 180-degree angles. It always has to be slightly more. What if space was the set of all ordered triplets of real numbers? Or r cubed? Well, now sides are polygons rather than edges, and sides meet 2 at an edge rather than 2 at a vertex. In 3D, diadicity is now no longer that 2 edges must meet at a vertex. It is now that 2 faces must meet at every edge. In every higher dimension, diadicity is when a polytope has 2 facets meeting at every ridge, no more, no less. A ridge is just an n-2 rank element of a polytope. For example, a vertex on a polygon, or an edge on a polyhedron, or a face on a polychoron. Lastly, the facet of a polytope is the rank n-1 element of a polytope, so it's equivalent to a side, like an edge of a polygon or a face of a polyhedron. If a shape lacks diadicity, it's not really a polytope. Wow, that was a lot of boring definition stuff. Well, back to the video now. Most videos about the Platonic solids explain Platonic solids by folding polygons up at a vertex to form a 3D solid. That's good, but I want to try something different for this video. Let's talk about n-dimensional shapes. N-dimensional shapes are any shape that exists in every dimension and have a clear mathematical definition. There's an infinite number of these, but let's look at 5. First up is the set of all points equidistant to the center. That gives us this shape. Okay, that's not a polytope, let's just ignore that. This is the n cube. It is formed by extruding the n-1 cube. So we go from a vertex to a line segment to a square to a cube, which is the first Platonic solid in 3D we've seen. Next up is the simplex. The n simplex is the pyramid of the n-1 simplex. So to take the pyramid of the shape is to place a vertex above it in the next dimension and then connect it to the original shape. So we go from a vertex to a line segment to a triangle to a tetrahedron, which is another Platonic solid. It has A3 symmetry, A for simplex and 3 for three-dimensional. What if we pyramid but like on both sides instead? We also have to change the height to try and keep things as symmetrical as we can, which we also have to do for the simplex, by the way. So this shape, called the n-orthoplex, is the bipyramid of the n-1 orthoplex. That sequence goes vertex, line segment, square, and then octahedron, which is another regular polyhedron. But wait, rewind a little bit. It becomes a square? Yep, in 2D, the n-cube and n-orthoplex are the same thing. Look at the cube and octahedron, though. The way they fit together. It's almost as if they have the same symmetry. And you'd be right, they do. This is the phenomenon of duals. Basically, the cube and the octahedron are duals of each other, meaning they have the same symmetry, but with vertices and sides swapped. On the cube, 3 fourgons meet at a vertex, and on an octahedron, 4 threegons meet at a vertex. That symmetry is called B3. B meaning cubic, 3 meaning rank 3. Kind of reveals the symmetrical nature of geometry, and how these shapes are just expressions of the imperceivable nature of symmetry groups, realized in a way we can understand. Oh, to gaze upon the mathematical perfection of B3, untainted by choosing the cube or the octahedron. Oh, I didn't know about this way of showing symmetry groups before writing the script. It's actually pretty good. In case you're wondering, the tetrahedron is the dual of itself. Anyway, moving on, we have one more n-dimensional shape. Alright, the last n-dimensional shape we're going to look at. This doesn't have a very good name, but it's often referred to as the joined n-cube. It's kind of complicated. Start with an n-cube. Yes, that's right, this shape is defined off of a shape from its own dimension, rather than the previous. Then we'll attach pyramids to every side of it, and adjust the height so that these sides become coplanar, or flush, with each other. In 2D, that just gives us the square, but in 3D it gives us a new shape. Wow! Look at that Hey, wait a second, that's not regular at all! I guess this n-dimensional operation is worthless for getting Platonic solids. Sorry, don't know how that slipped into the script. Okay, so that's all the n-dimensional and simple geometric operations we can do to get the Platonic solids, but there's still 2 more Platonic solids. We do actually need to fold polygons to get these. So if we have some triangles here, notice how they don't fully close, and there's more than 2 of them. This means it can be folded into 3D to start a polyhedron. And would you look at that, we get another Platonic solid, the icosahedron. It has 20 triangular faces, and they meet 5 at a vertex. So if we flip that around, 3 5-gons at a vertex, do we get the dual? Yep, we get the dodecahedron, the 12-sided and subjectively prettiest Platonic solid. These both have H3 symmetry. This is how it looks folding up, by the way. Okay, I think we've learned enough that we're ready to explore what it means for a polytope to actually be regular now. Most people explain regular shapes as every vertex, edge, face, etc. being the same, but I've always found this to be vague, since in my mind the only way an edge can be different is to have a different length, and all vertices are identical. So usually what they mean is the neighbors of an edge or vertex need to be the same for every vertex or edge. This is a superset of a more specific idea called vertex or edge transitivity. Basically, if something is vertex transitive, it means I can transform any vertex to match any other, and the shape will look identical. There's only one shape I know of where every vertex has the same neighbors, but it's not vertex transitive, and it's this goofy shape, called the pseudo-rhombocubooctahedron. Look, every vertex has the same neighbors, 3 squares and a triangle, but as you can see, it isn't vertex transitive. Edge transitivity is the same thing, but with edges. So is that what it means for a polytope to be regular? That it's vertex, edge, face, etc. transitive? Nope! It is slightly more complicated because I'm gonna pull a Diogenes. Hey guys, look at my regular polyhedron. Guys, look, it's so regular. It has vertex, edge, and face transitivity. This property of having all the transitive properties possible in that dimension is called being weakly regular. Compounds, which are often excluded from being considered polytopes because their edge graphs are disconnected, can be weakly regular. So what's this mysterious property that separates the weakly regular polytopes, like the rhombus tiling, from the true regulars, like the dodecahedron? Flag transitivity. A flag is where you have an element from every dimension all contained within each other, like this flag of the cube. Then it just works like other transitivity rules, where you have to be able to transform this shape to move any flag to any other. This excludes the rhombus tiling and all other weakly regular polytopes. It makes a lot of sense to say that the elements and flags of a regular polytope are utterly indistinguishable from each other. Well, that was a lot, but now you know what regular actually means, completely. One last thing before we go up to R4. Remember that shape folding we did? Well, we can plot all the Platonic solids on a table like this, and we notice some missing spots. These can actually be filled with alternate geometries. See, when we talk about polyhedra, we're really, usually, talking about tilings of 2D spherical space. Well, what about tilings of Euclidean space? There are 3 regular planar epirahedra in 2-dimensional Euclidean space. There's the triangular tiling, the square tiling, and the hexagonal tiling. It might seem weird to say 2-dimensional Euclidean space. After all, these are polyhedra, but remember, when we have polyhedra that are tilings of the sphere is a 2-dimensional space too. Also, you might think that the weird part is that I'm calling them polyhedra. The reason is, what else could they be? Since they're 2-dimensional, you might want to call them polygons, but they have 2-dimensional faces. And remember, the rank of a polytope is simply the rank of its facets plus 1. And since this has rank 2 facets, it's obviously a rank 3 polytope, or a polyhedron. So it's the rank that determines the n polytope, not the dimension. So these are 2-dimensional polyhedra. Sometimes the dimension can even be higher than the rank, like with this crazy thing. While these are regular polyhedra, they aren't Platonic solids because they aren't convex nor are they finite. But they are regular, and the more you think about polytopes, the easier they are to accept as normal. They're the only polyhedra with translational symmetry, which is kind of neat. Kuvina has a great video on these polyhedra if you want to learn more. Anyway, as you can see from the chart, the triangular and hexagonal tilings are across from each other along the diagonal, so they are duals. It makes sense. The triangular tiling is 6 3-gons to a vertex, and the hexagonal tiling is 3 6-gons to a vertex. Lastly, the square tiling is dual to itself, since it's 4 4-gons around a vertex. There's a cubic tiling in every dimension, and it's always self-dual. These polyhedra violate the idea that polytopes can be described as sets of points in space, because they'd all be the same set, which is sad. Oh well, it was fun while it lasted. Anyway, this isn't a video about regular polytopes. It's about Platonic solids. If you want regular polyhedra specifically, just watch Jan Miesely's video. I know I'm going to get comments from people who saw that video and misinterpreted him as saying there's 48 Platonic solids anyway. Man, poor Jan Miesely, being misquoted everywhere until the end of time. Now, I know what you're going to ask me. There's 8 empty cells here, and if you extend it further, there's an infinite number of missing cells. Well, this region is spherical tilings, this region is Euclidean tilings, and everything past is hyperbolic tilings, which I absolutely do not have time for, so don't ask. But I do have this chart. Okay, there's no more Platonic solids here. One last thing before we go to 4D, and it's that I want to see all the Platonic solids fold up. Let's jump up to 4D now. In part 2. This video is getting way too long. I put so many hours of work into this video. Make sure to dislike, unsubscribe, and purposefully not leave a comment to spite the algorithm. Let's get this video to be the least watched video on YouTube, guys.